Hey, what's going on, guys? Today I'll be going over coin change, and in this problem you're given an array of coins and an amount, and then you have to find the minimum amount of coins that will take to sum up to that amount. So the brute force algorithm of this problem would be just to check every single possible combination in this coins array and see if that combination adds up to the amount. And this is a very inefficient solution, and you'll probably time out before you even get to a solution. So let's take a step back here. So what you'll notice about the coin change problem is it's very similar to the knapsack problem. And if you're not familiar with the knapsack problem, you're essentially given a set of items, each with a weight and a value. You have to determine the number of each item to include in a collection so that the total weight is less than or equal to a given limit. So essentially, this coin change problem is the knapsack problem, just to reword it a little bit. So the weight would essentially be the actual values inside the coins array. So like, let's say 5, this coin has a weight of 5. And the value in this case would always be 1 because each coin is always counted as one coin. And then the given limit would essentially be our amount value that we're trying to get to. I'll admit that this problem is actually very difficult if you don't know how to go about approaching it, but essentially the method or the algorithm you want to be using is dynamic programming. So you want to have a DP array where the index would essentially be the amount, and the value of each index would be the number of coins required to get to that amount. So for instance, our first index here would be index 0, also the value is 0. So essentially what that means is how many coins does it take to add up to the amount 0, right? And essentially it's 0 because we don't have, or we don't need to add any coins to add up to 0. And then for the next index, it's basically the amount of coins it's gonna take to add up to the amount 1, and then 2, and then 3, and then 4, and then 5, all the way up until we get to the amount equal to 11. So this amount right here, this last element in the DP array, is what we actually want to be returning. So the initial state of the DP array will be 0 for the first index because that is already a known. We know that to get to the amount 0, we need 0 coins, and then the rest of the array will be filled with a value above the amount. So right now, it's just filled with the amount plus 1, but keep in mind this can be like any value that is above the current amount. So essentially, the 12 right now is marking an invalid state. So an invalid state is when the amount is impossible to reach with the given coin values. So let's say our amount was 1 and we didn't have this 1 in the coins array. That means it's impossible to get to, so we need a flag to signify that. And that flag would just be amount plus 1, but then again, you can use any value that's greater than the amount. So what you'll notice right now is that everything is marked to invalid, and what we want to be doing is looping through this DP array and changing the invalid flag to a valid one when necessary. So let's start by going through the first iteration. So in the first iteration, we start at this index here, and then we want to loop through the coins array, right? And then we're essentially going to only update the value in the DP array when this condition is true. So this condition is if coin is less than or equal to value. So that makes sense because let's say you have, in our case right now, the value would be 1, right? So we don't want this 5 if our amount is 1. It's impossible to get to the amount 1 with a coin 5. So then we can skip over that coin value. So we're going to loop through the coins array, and we start with 1 here, and 1 is less than or equal to value, and value is equal to 1. So then this line of code runs. So we update the value in our DP array. So what do we update it with? We update it with the lesser of 2 values. right? So we're doing lesser because we want to find the fewest number of coins that make up the amount. That's why we use min here. So the lesser of two values, either the current value that's stored there, which in our case is 12, or dp bracket value minus coin plus 1. So where do we get this dp value minus coin plus 1 from? So we do dp value minus coin because we are essentially subtracting the amount by the coin each time it's selected, right? So in our first iteration, dp value minus coin is equal to 0. And we do plus 1 because the plus 1 represents the current coin that you're selecting. So since it's a dynamic programming problem, we're always going to be using our previous elements to calculate our current element, right? So in this case, the previous element would be dp of 0, and that is just 0. So we do 0 plus 1. So that makes sense, right? Because we're finding the value, the amount of coins it takes to add up to the amount 0, and then we're doing a plus 1 to it for the current coin, right? If it doesn't make sense now, I promise you it will make sense later. So essentially at this point, we want to update that value to 1, and then we move on to our next iteration. So for this iteration here, value is equal to 2 because we're at the second index, and now we loop through our coins array and we start at 1. So in the case of 1, we're choosing the minimum of two values, either 12 or this dp array value minus coin plus 1. So let's calculate that real quick. So dp of value is 2 minus coin. Coin is equal to 1 right now, so dp of 1 plus 1. So dp of 1 is 1, and then we have that plus 1, so then that's a 2. And this dp array would update to 2, but we're still going on with this for loop, right? Because that is, we can actually find better answers than that. We're not done yet because we're not done iterating through the coins array. So then now when we get to the value 2, we look at this line of code and we're choosing the minimum between the value 2, which is what's currently in the dp array, or the dp of value minus coin plus 1, which would essentially be, this would essentially calculate out to 1. So then dp of value becomes 1. So this line of code here is very important, and this dp value minus coin plus 1 part is where we're essentially taking a previous solution and then adding 1 to it in the event that you're actually doing the selection, right? So say we're at index 3 now, so to find the optimal number of coins it takes to get to the amount 3, we're going to use the optimal number of coins it takes to get to these previous amounts to calculate that. So again, the second parameter here is where you're actually selecting the coin. So when you select the coin, that's where you get the value minus coin, because you've already selected it, so then you have to subtract it from the amount, and then we use that previous solution to calculate our current solution. So we do plus 1 to add the current coin. So we're eventually going to get to the point where the value is equal to 3 and the coin is equal to 2, right? So value minus coin is equal to 1. So we look up our previous solution. Our previous solution is this number 1 here. So this 1 represents the minimum number of coins it takes to get to the amount 1. So there's only one way that we can get to the amount 1 with these coin values, and that's with just selecting a single 1, right? And then we have to account for the coin that we're adding, right? So the coin that we're adding in this case would be 2. So once we add the 2, that means the minimum amount of coins is going to increase by 1, hence we have this plus 1 here. So if you continue on with this algorithm, you will essentially get to the point where you have every single amount value calculated up to 11. So this value 3 here would be the number of coins, the minimum number of coins it takes to get to the amount 11. And we would essentially check to see if that index value is still 12. In the event that it's still 12, it means that it's invalid, right? So if it's invalid, we return -1. But in the event that it's not, we return the value stored in that index, which is 3. So that's what we return here. So our answer would be 3. So going over the complexity real quick, the runtime will be n times m, where n is the size of the coins array and m is the actual amount. And the space complexity is O of n because we just have a DP array that we're trying to fill out. And that's pretty much it, guys. Thanks for watching, and I'll see you guys in the next one.